In this video, we're going to take a look at Chapter 5 on how force affects motion. So these are the objectives that we're going to go through here quickly in Section 1. And a lot of this is going to be review from AP Physics 1, but we're going to incorporate some of the new things here with how the calculus gets involved. So first, as a quick review, a force is a push or a pull here that acts on an object. And the main thing is that it causes an acceleration. Now we're going to focus on Newton's 3 laws of motion, and we call this Newtonian mechanics. Now it's valid for everyday situations. It's not valid when we get to really high speeds, and we'll talk about that in a later unit, specifically when we approach some fraction of the speed of light. And it's also not valid for really small things, such as on the scale of the atomic structure. So we can look at it for everyday situations, and we say it's pretty much an approximation of general relativity. So before Newtonian mechanics came onto the scene here, there was Aristotle's point of view, where he felt that some influence of force was thought necessary to keep a body moving. There was this idea of a natural state of objects was at rest, and so this was intuitively reasonable because if you watched things in everyday life, they would eventually come to rest. Now this was because of friction, and so they weren't really thinking about what friction was, or even the idea of a frictionless surface. And so if we envision a frictionless surface, we can see that objects do not slow down just naturally. They need a force. And so that tells us that friction is in fact a force. And Newton's first law tells us that if there's no force on a body, then the body's velocity cannot change. We know that the units of a force is a newton, and 1 newton is a kilogram meters per second squared. And we say that the acceleration of a mass is proportional to that force that is exerted, or the net force. And net force is just the vector sum. So we're going to look at forces as vectors in vector notation, add those together to get our net force. And we know that if there is no net force, then we say that the object is in equilibrium and the body's velocity will not change. All right, and this is taking us back to Newton's first law. So one thing that we need to talk about here, though, is inertial reference frames. And we didn't get into this too much in AP Physics 1. But basically, an inertial reference frame is just one where Newton's laws hold. All right, and we can still observe Newtonian mechanics. Now, typically, we say on Earth that we are an inertial reference frame. However, that is not the case when we're looking at very long distances, because the issue here is that the Earth is in fact rotating. And so because of that rotation, if we were to, let's imagine a really long patch of ice, and we're, so it's essentially frictionless, and we slide a puck down it. Now we would expect that to continue along a linear path, and for short distances it will. However, if we go a long distance, we'll actually see that puck start to deflect off of the linear path. And so it makes it look like there's a force that's happening, but really all that's happening is that the Earth is rotating and the puck is continuing with its inertia. But from our reference frame, because we're rotating with the Earth, it looks like the puck is actually deflecting, and there's some fictitious force. So in that reference frame, we say that it is not an inertial reference frame because Newton's laws do not hold up. So here's a quick little checkpoint. It's pretty basic, just asking which one would actually yield the third vector. And we're pretty good at adding vectors at this point, so we know that C, D, and E are the only ones that actually result in a third vector as shown. So in Newton's laws, we need to talk about the difference between mass and weight. And hopefully we have a good idea of the difference between these two. And we say that the mass is a characteristic of the object, and it isn't dependent upon its location, and it is not the same as its weight, density, and size. However, it is inversely proportional to acceleration because of Newton's second law. And so Newton's second law tells us that the net force is equal to the mass times acceleration. Now we're going to keep that same law, use it the same way we did as in AP Physics 1. However, we are going to look at these as vectors. All right, the force is a vector and the acceleration is a vector. And so really mass is just a scalar multiplier. And we can look at things in their components, looking at the net force in the x direction is equal to the mass times acceleration in the x direction, and so on. And so we can look at these separately in each dimension, but we can also look at it as a vector and just use the mass as a scalar multiplier. And we know if net force on a body is 0, then the acceleration is 0. And so we call that equilibrium. But we have to remember that doesn't mean that there aren't any forces. Just because something's in equilibrium, there still may be forces on it. We just know that the forces are in fact balanced. Now, table 5.1 here is kind of nice to tell us the different units of force. Now, typically we're going to use newtons, all right, because we're in the SI system, so newtons, kilograms, meters per second squared. However, if you're in the CGS system, then the force is actually called a dyne, which is a gram centimeter per second squared. And then in the British system that we use in this country, it's called a pound. Okay, so a lot of times when we're solving these problems, we need free body diagrams. So whether it's 1 dimension, 2 dimensions, or 3 dimensions, we need a free body diagram. What are the forces acting on the object? Couple things to remember in a free body diagram: only one object at a time, and we're only looking at the forces acting on that object. Okay? Never, never, never put acceleration on the free body diagram. Now, you may want to denote the direction of acceleration if you know that, but you don't put acceleration on the diagram. And it's important to set up some type of coordinate system, whether it's given to you or you create it. So in this situation, we have this figure here, 5 newtons to the right, 3 newtons to the left, and we want to know what are the magnitudes and directions of F3 when the block is stationary or when it's moving to the left at a constant speed of 5 meters per second. Well, if F3 is going to cancel out these forces, it has to cancel out this net force. This has a net force of 2 newtons to the right, and so F3 has to be 2 newtons to the left in both cases, because each of these are in equilibrium. Stationary, and constant speed both have an acceleration of 0. So when we're talking about a system, we're talking about something that has one or more bodies in it. So 2 objects that are interacting. And any force on the bodies inside the system exerted by bodies outside, we call those external forces. All right, net force on the system is the sum of all the external forces. Forces inside, or the internal forces, we do not include those on a free body diagram. So because of this, this actually can help us. We can eliminate some forces that we don't know if we make our system big enough so that to cause some forces to become internal, which we can then eliminate. Okay? Now, don't confuse, this is important down here, don't confuse a free body diagram of an entire system with the free body diagram of individual bodies. So we will look at the diagram of a system, and then there's times that we'll go deeper into that system and look at diagrams of individual bodies. So let's look at a couple particular forces that we know. Force of gravity, we know that's m times g, and we're going to use the notation F sub g, all right, sub baby g there, to know that it is the force of gravity, and this is a vector, right? And we know this is always towards the center of the Earth, so if we use our typical Cartesian coordinate system, it's just negative mg j hat, all right? Or we can say that g is its own acceleration vector, where it has that negative j hat component. All right, we call this the weight, all right, the force due to gravity, we call it the weight, so oftentimes we'll even use a capital W as our force for the weight here. All right, and so we know that that's just the mass times baby g. So this gives us that relationship between weight and mass. Now, measuring weight, we typically use a balance. We compare it to known masses. We can use a spring scale to do that. The issue with the balance is this is actually measuring the normal force, so we'll talk about that in a second. So it does not work in an elevator. All right, because if there's acceleration, then the normal force changes, and that's not actually measuring the weight. If we're at rest, then a balance, or a scale will work fine. Okay, and so normal force, this is always perpendicular to the surface of contact. Anytime there's 2 surfaces in contact, there will be a normal force. Oftentimes, we'll look at some of the forces in the y direction, and so we get this nice equation here that the normal force is equal to the weight plus the mass times acceleration, which typically we're not accelerating in the y direction, so the normal force is going to be equal to mg. Okay, and looking at this little check here, we see that we're equal to mg when there's no acceleration, but we're greater to mg with positive acceleration. All right, so if we have positive acceleration, our normal force is going to be greater. Another particular force is friction. All right, we'll spend a little more time on friction later in this unit, but for right now, we just need to know friction is going to oppose the motion. Okay, and we're just going to deal with kinetic friction right now. That's opposing the motion, and there has to be sliding between those two contacts. And then we have tension, and so tension is going to be in a cord, a rope, a chain, something like that. And if it's massless, we're going to have the same force throughout the cord or the chain or whatever it is. When it does actually have mass, and we'll look at that in a later unit, that's going to change things, and the tension will change throughout the cord. All right, and so here's another quick check here looking at something that weighs 75 newtons, and if we're pulling at a constant speed, increasing speed or decreasing speed, how does the tension vary? Well, we know that it's equal to 75 when we're constant, greater when we're increasing speed, and less when we are decreasing our speed. So looking at applying Newton's laws here, we need to take a look at Newton's third law, and we know Newton's third law for every action. There's an equal but opposite reaction, and so we have these Newtonian pairs, and so we're going to use this notation here and use our subscripts to describe what's happening. And so this FBC, this is the force on B from C, is equal to the force on C from B. Now these are talking magnitudes here. So we know their vectors are going to be opposites. All right, if we just multiply by the scalar multiplier of -1, we get the same vector. Key thing here is anytime two objects interact, there is a third law force pair, and these are on different objects. The Newtonian pairs are not going to be on the same object. So if we have this cantaloupe that's sitting on a table that's on Earth, well, what's happening to the cantaloupe? Well, there's the force of the cantaloupe, the force on the cantaloupe from the table, all right, which is going to be equal to the negative of the force on the table from the cantaloupe. But then there's also the interaction between the Earth and the cantaloupe, all right? So the Earth pulls on the cantaloupe, but the cantaloupe also pulls on the Earth. All right, so any force, there's going to be a Newtonian pair, even friction, and that gets a little crazy a little later, but every force has a Newtonian pair. Okay, we're going to skip this one for right now, but if you wanted to read over it and look at the answers, that's fine. It's a decent practice for talking about Newton's third law. I do want to show this diagram here in some nice simplified equations for you, because we're going to look at this situation a lot, where we have a mass that's sliding on a table, and it's sliding because we have a weight that's connected to a string in this pulley here. Okay, and so if we look at the forces, well, what's happening on block S and block H? We have these two different blocks, S and H, and we call the mass of block S big M, the mass of block H little m. And so we see we have tension, normal force, weight of gravity, all that stuff. And so applying Newton's laws to these and looking at these free body diagrams, we can come up with these nice handy equations. And so these are actually equations that we're going to use a lot when it comes into play with this type of situation, with the block on the table and one that's hanging. So the tension is equal to the mass times acceleration of the big block on the table, and if we subtract the little mass, the hanging mass here, and subtract that from tension, that's going to be the negative of the mass times acceleration of that little block. And then here are also two very handy equations or simplifications of Newton's laws being applied to this situation here. Okay, now in this example, I think we were given some mass, and so we can actually find those numbers. But these equations are ones that we're going to use in the future. Okay, also I want to direct you to figure 515. Okay, it's in the book when you did the reading here. This is looking at anything that's on an inclined plane. All right, this simplifies things nicely for stuff on an inclined plane, whether we're pulling it up, pulling it down. And this diagram helps us with our trig, triangle, in splitting up the weight of gravity or the force of gravity into its components on an axis along the ramp. And so that's beneficial for us to do that along the ramp. So we're going to continue to practice this stuff in class with some other examples.